energy is dissipated in the system. Only 7% of the energy of the heart is dissipated in the veins. All the rest is where I told you, in the arteries, in the arterioles, in the capillaries. If you go on the other side, you'll see where the blood is stored at all times. You'll see that it is stored mostly in veins. And the heart has a certain percent, and all the other organs have about equal amounts of blood. On the other hand, if you look at the different organs inside the diagram, you'll see that the brain and the kidney, compared to their weight, they consume most of the circulation. Do you see that? Yep. Any hands? Good. Okay. And in terms of the brain, well, one would expect that the king of them all would die last. In other words, he's about to give up the whole kingdom before he dies, and this is true. About 15% of the circulation goes to the brain and is consumed. The brain has tremendous amounts it dissipates tremendous amounts of energy. But the kidney now requires a lot of blood, not because it needs it to survive on it, but because this is the job. The job that the kidney does is to keep the homeostasis. Remember when we talked in the first lecture about the homeostasis? To keep the homeostasis of the blood, and in order to do this, it has to take out and put in different substances to the blood. And this it does continuously. So about 20% of the circulation also goes there. So, we are going to go into now some very interesting talking about how does the heart achieve its pumping function. Before we go on, any questions from what we discussed up to now?
No.
No? Okay, you want to take a few minutes break here?
Sure. Yes.
Okay, let's take a few minutes break. We're not going to turn off the connection. We'll just take 5 so that you know, we're getting into a different chapter now. We're going to try to start getting into mechanical things. So I think this is okay. I see somebody stretching really good. 2. So how is life in Varna? We have great weather down here, by the way. Next time I'll have a camera outside. I'll show you a few pictures of our university. But I'll probably see you before that.
Are you in the university or are you at home?
No. Does it look like home? No, I'm at the university. Next time I'll do it from home on an internet basis. This is not internet. This is done through ISDN, through telephone wires. Yeah. How is life there? What is it raining or is it sunny?
No, today is beautiful.
Beautiful. Huh?
Yeah.
I don't know whether it is the climate change or indeed we are very lucky.
I didn't hear him.
No, I said I don't know if it is the climate change that makes the temperatures go up or we're just lucky. But normally this time of the year we get snow, but doesn't look like.
We heard the same thing. It seems to be very cold in this time of the year. But I think it's us. We're bringing good luck to Europe.
Yeah. So how are the other courses going on? Okay?
When did we get there?
Okay.
So it's part of the required.
A lot of work.
Because catching up.
It was
Trying to catch up.
Well, listen, the first semester, you're pioneers. You have to look at it from that standpoint, that you're really pioneers. But,
Pioneer anything.
so we are going to take good care of you and make sure that you succeed. This is going to be the positive part of it.
Oh,
It's the same author, but it's like a review. It's like a board review or something.
it's for the USMLE.
You have some questions from the board reviews there? Does somebody have a book from board reviews?
Yeah.
Takashi.
Takashi.
Your friend.
Okay, so how do the questions that I sent you for the first part match with those?
Did you check?
You cannot open them?
Yeah, because I already use the internet cafe, so I cannot.
Well, no, hold on. I have sent them to Aneta. She was supposed to print them for you. Didn't you get those?
We have not received
Ask Aneta because she was supposed to print them and then make photocopies for everybody. I mean, I'll send them to you.
She said she has, we just haven't gotten them yet.
What she hasn't gotten? The questions?
She did say they were printed out. I think she just hasn't given it to us
I
yet.
see, okay. Because I am preparing a second set to send you that will cover the cardiovascular now, but and those are, also complicated questions. Once we get out of the basic physiology, things get they get a little bit more complicated, but they are easier to understand. The concepts, I think, are easier. I think the smaller the level that you're looking at, the closer to the membrane you are, the more difficult sometimes things are. What is this nice thing you're eating there?
They're eating almonds.
Almonds, ah. Here I'm stuck with coffee and water. You have almonds.
So are we having a midterm in physiology?
Why shouldn't we?
I'm just asking, or if we do, when do we have it? In December?
When you have all your midterms, what I'm going to do, I'll tell you what I have in mind, but I want to discuss with you. And now there are only 3 of you there, but that's okay. The rest, I suppose, they're around. My idea is that I will use for the midterm the material that I already have. I mean, the material that you are going to have to cover for the exams is the general physiology and the cardiovascular physiology. And stop there. I mean, blood and renal physiology that come next, I'm not going to, even if we go into that, I'm not going to go into the midterm. In fact, wherever we stop today will be the material that you have to read for and worry about for your midterm. And all the rest can go for the final. Okay. I think this is fair on you because this is the worst part of the semester for you. You have to adjust, you have to read, you have to change classes every other day, so there is no reason to push more material on your shoulders at this point. That's number one. And number two, traditionally the midterm covers about 1/3 of the total amount that one should cover in a class. At least in my time in Berkeley and in UCLA, that's how we used to teach. When I was a teaching assistant, we normally had 1/3 of the material for the midterm and the full 3/3 for the final. I don't know what's your experience nowadays. I haven't taught in the States for maybe 15 years, but has anything changed in that philosophy?
No, I think it's pretty much the same. 1/3 to almost a half.
Well, I prefer to stay, in other words, where we finish today, whatever it is, we'll draw the line and we say up to this point. Is that fair?
Yeah.
Yeah.
Okay? And I'll try to send you questions for the cardiovascular no later than next Saturday.
Okay.
All right?
And then, are you making the midterm or are you going to receive the questions?
Nothing.
Well, I think there are two ways. I think that one way is to send the questions, because to come just for the midterm is, you know, it's not that it's not nice, but I have nothing else to do. I should not be teaching at that time. You have too many midterms on your head. On the other hand, I wonder whether you want to use the time to discuss everything that has gone through the midterm and up to the midterm. And in that case, yes, I will come, but I mean, this is up to you, whatever you decide.
It's up to us if we want.
To review the material.
Oh, before the midterm?
I will review the material and I'll definitely go through the. But you see, if I get the midterm, I can, you know, I can come there, administer it one day, give you the results next day. I mean, if I have to, this is easy. After all, it's multiple choice questions. But the point is, okay, will you have at that time to sit down with me and discuss why this should have been this way, that way? Because all of you will have some questions. I mean, this is, but you'll have other midterms at the same time, isn't it so?
I think, can we have a review, like with those questions that you sent it to us?
We'll.
Questions that you will try?
What, I didn't hear the last one. Yes, we are going to have a review of your midterm results. And all the questions that went into the midterm, we are going to discuss them. My question is, should we do it during the midterm period or wait until the next lecture?
The next lecture is fine.
I think so. I mean, because you'll have other midterms going on, isn't it so?
Yeah.
How long do they give you for the midterms? 1 week?
They haven't given us the dates yet. We're not sure at all.
No, I know the date you don't have, but how long will the midterm period take?
Even that, they haven't told us that.
You see, normally I would think that in your case at least you should have like a week in which to administer all the midterms and have time to study and get yourself, you know, in shape. For my part, I said for the midterm, whatever we do up to this afternoon, and then you're going to get also a full set of questions, so you have at least 15-20 days to study. I don't think the midterms are next week, right?
No.
Yeah, for sure should be like 20 days from now. Yeah, that's fine.
20 days, so you'll have my results within 6 days, 7 days, I mean my questions, so that you have another 15 days to prepare for them. And you already have the ones for the first part.
Okay.
Okay? Now I'll tell you something else. If you promise me that you'll read the questions, then I'll put half of the questions from what you already have in your hands, at least.
Okay, that's good.
No, but no, listen, I'm not trying to be nice to you, but I think that if you know those questions, you are entitled to the bonus of having worked for them. It's simple as that. After all, no matter what you do in your midterm or further down the line, doesn't matter. It is what you do at the real exams that matters, and this is what I have to prepare you for. Anyway, I think 5 minutes are up. About 5 minutes ago. Should we go on?
Yeah.
Okay. So the question is, how does the heart achieve its pumping function? Okay. Now, what is a pump? A pump is a machine or device, as they say in the dictionaries, for raising, compressing, or transferring fluids. Now, these things come from real life, okay? They are part of a Webster type of definition. And they talk about raising because in the United States, when they talk about pumps, the first pump that comes into their mind, believe it or not, is not the water pumps, or rather it is water pumps and oil pumps, and those raise water. Okay? But also they are there for compressing or transferring fluids, which is the real definition is transferring fluid. Now, there are many types of pumps. Believe it, there are more. I can sit here and rattle about 12 kinds of pumps. Not that I studied pumps, but I have gone through that many in my life. Pumps with the cars, pumps with the in the laboratory. Laboratories use a lot of pumps, by the way, different types. But there are, some pumps you definitely will hear about is jet pumps, centrifugal pumps, piston pumps. Okay, there are other types, but these are the ones that you are going to listen and hear about. And I like to say that the heart is like no other pump, but it is based on the same principle as the piston pump is. And I'll explain to you why. Now, don't start looking for where you have the piston inside your chest. You'll not find one, okay? All I said is that the principles are the same. Well, here as you see a jet pump where you have a high pressure fluid going in, and this creates a vacuum on the other side that pulls fluid from one side to the other. This is, I'm sure all of you have seen a jet pump. You know where? You have seen it in the laboratories where we stick a little device on a faucet to create vacuum, right? Water comes where you see the high pressure fluid going through, and it sucks from a side air. So we create vacuum. This is in every chemistry laboratory. I'm sure that there is at least one faucet that has such a pump stuck on it. So in order to make it work, all you have to do is turn on the water. You recall that from your days in the laboratory? In college? No?
Yeah. No, I don't.
Yeah? You recall it, right? The other one is, what you see is you have a rotating pump where you see this fan type of thing that goes in, but it's not like a fan in the regular sense. It's called an impeller because it pushes the water in one way and it pulls the fluid in from another one. It looks pretty much like what they used to do in the Shenandoah boats down the Mississippi River. This is how they used to propel them. Remember those big things that they were running? They were paddling the water. Have you seen old movies? Mm-hmm. Okay, this is the same principle that works here. Excuse me. On the other side, you see the piston pump. The piston pump has two characteristics. First of all, it has a chamber that through a piston it increases in size or decreases in size. Okay? And that chamber gets filled or emptied through two valves. And the valves are set up in such a way that the flow is always unidirectional. Now what you see there, as the piston pushes down, the pressure increases in this middle chamber and it pushes the bottom valve down so the fluid cannot backtrack into the pipe that comes from the bottom of the picture going up. You see it? Yes? Or no?
Yes.
Okay. And at the same time, if you notice the top valve, it's easy to open up because it's going through the direction of the flow. So if the piston goes down, it reduces the area in the chamber and it pushes whatever is content in the chamber, it pushes it towards the pipe that goes up from your picture. Right? when you reverse and you start increasing the area in the chamber, the pressure drops, the top valve is sucked back, and it does not allow backtracking, while the other pump now can go up because it's sucked in, and water or fluid can go from the bottom part into the chamber. So the continuous back and forth of this thing pumps the fluid from the bottom of the picture all the way up. Is that understood?
Yep.
The characteristic in this picture is not the piston. The piston serves only one function, to increase or decrease the area of the chamber that you see there. And this is why I say that the heart works like a piston pump, because the chambers of the heart increase or decrease the volume they contain. Okay? I want you to really understand this. You know, simple as it may sound, the reason I insist on understanding these simple things is because they do get complicated very fast if you don't understand them, number one. And number two, physiology is very simple, believe me. And you'll have to remember less the more you understand. That's all there is to it. Okay, let's go to the next slide then and see all these things written down. Okay, we say that we have a chamber which is a variable volume chamber. And this is the two distinguished characteristics of the piston pump. The variable volume chamber, which is due to the piston movement, and the valves at the entrance and the exit of the chamber. These permit unidirectional flow. And the unidirectional flow is the crucial word that you want to remember here. Why? Because this is exactly how your heart is made. Well, we already talked about this, but it is the myocardium that acts to reduce the surface of the chamber, and thereby, if you reduce the surface, you reduce the volume. Keep this concept in mind, you will need it, because when we talk about the cardiac cycle, that is, how does the heart pump the blood, this becomes very important. Before we go any further, let's just take a minute here and come back to what we had discussed about cells. Sorry, I refer you back to cellular physiology all the time, but believe me, it really helps to understand the concepts very clearly, and then you can build on them in your mind. Let's go back to a cylindrical cell that represents a muscle cell. Okay? What happens during the time that this cell contracts? What happens to the length of the cell? Come on, what happens to the length of the cell when it contracts? Nobody will tell me? It shortens, it decreases, correct? But,
Yeah.
but what happens to the volume of the cell?
Decreases?
What?
Stays.
Decreases. Did I hear decreases? Who agrees that the volume of the cell decreases during contraction? Raise your hands so I can see you. 1, 2, 3, 4, 5. Come on, an engineer. I see an engineer putting her hand up and down. Come on, guys. I should never expect you to get answers like that. The volume never increases nor decreases. It's full of fluid. Fluids are incompressible. Therefore, the volume will remain the same. So, what happens to a cell that contracts? It gets short and fat.
Yeah.
Oh yeah? Takashi.
Explain to us.
Right? When the cell contracts, it gets short and fat. Therefore, it's not only the surface of the chamber that decreases because the length of all the fibers decreases, but also the fact that the cells protrude their bellies inside. So they reduce further the chamber. When, in other words, the chamber, the tissue contracts, the diameter of the wall increases. Now, no book says that, and for the life of me, this is a source of confusion that every time I ask someone, he has some other question. Think about it, because we need it when we talk about the chambers of the heart. Okay? So, when you decrease the area of the chamber, the volume inside will decrease, but the cellular volume, the volume of the muscle will remain the same. It's not going to change, correct?
Correct.
Understood why? You'll not find it in your books. I don't know why they don't write that. They consider us very, very smart, all of us. But anyway, let's go on. What was the question, please? What was the question? Here is none of them.
There's no question.
Oh, we were just discussing what you just talked about.
We didn't understand the question at first. We didn't talk about the muscle volume. We talked about the chamber volume.
Oh, okay. Well, I shouldn't scold you then, but it's okay. I agree with you. The chamber volume decreases, but the muscle volume remains the same. Okay?
Yeah.
But the surface decreases. The interior surface of the chamber decreases. Okay? Now we are all clear on that, right? Okay. Now, let's go to the next slide that says, in contrast to the first, that the heart does not have a piston, but it uses its own wall to increase and decrease the size of the chamber, it does have unidirectional valves. Okay? So, this is exactly what happens. When the valve opens, it allows the movement to go on. When the valve closes, it does not allow backtracking. This is what a unidirectional valve is. Now, take a good look at this, because you are going to see the same system working in your veins. All your large veins, and the small ones too, to a certain degree, have valves that do not allow the blood to go back. Otherwise, we would all have, our feet would be round balls because of all the blood sitting there as soon as we stood up. It is those valves that allow us to maintain our circulation. And also, do not forget that if you move around, your feet do not get tired as much as if you stand in the same place. This is because the blood keeps circulating, because it is pumped by the action of the muscle around it up, and those valves do not allow it to backtrack. Anyway, we're going to talk about this later. Right now we're interested in this concept only for the valves of the heart. Okay? So, in this, you'll see a little diagram where you see the 4 basic valves of the heart. We said there are 2 chambers, 2 pumps, and therefore we need 4 unidirectional valves. And you see down below in the diagram the way the valves look. some of them have 3 and some of them have 2 cusps, and we can easily discern on this diagram the aortic valve, okay, which is right there in the middle of the diagram. You can see it where it is, right? And then the pulmonary valve, and these are in the forward part of the heart. That is, those are the valves. If you recall this green diagram that we had with the piston pump, these are the top valves in the diagram. You want me to go back and show you the diagram? You see this diagram? The aortic and the pulmonary valves are the top in this diagram, okay? The top valve. And the right and left atrioventricular valves are the bottom. Because they close whenever this chamber contracts, right? Now you are going to see this in many anatomical books and in your anatomy class and everything else. So you have no real problem there. But this is a diagram you better remember at least schematically. All right? Any questions up to now? Okay. If you cut the heart across it, that is in a fairly parallel sense to your in a sense perpendicular to your torso, or let's say about parallel to your diaphragm, and if you cut right about where the place where the heart separates on the outside the ventricles from the atria, and that is about where the vessels of the heart are, okay, you're going to get a picture like this. You can see rear and front and rear, okay, so the face of the person is looking down on this thing, okay, and you're looking at it from the top, as if you're looking at the person from his head down, from his head towards his feet. Then you see all the 4 valves in one plane, and 2 of them go from top down, and these are the right and left AV valves, the big ones there, okay, with the big fibrous rings around, and the other 2 go from bottom up. This is the aortic valve and the pulmonary valve. This to complete the diagram that you had in the previous slide. Now, this is another view of where you see the valves. Now you understand what I was saying probably about getting the way the cut should be in order to see the valves. All right? And keep this in mind, not for the reason that we're talking about the valves, but keep this about this fibrous skeleton. This fibrous skeleton, which extends in the whole plane from one side to the other. In other words, let's go back a little bit. You see on this thing, between this fibrous skeleton, between the rings, you see this yellowish fibers in the middle. Do you see it on this diagram? In the center, you see these yellowish fibers going up and down from rear to front, and opening up, fanning out. Do you see it?
Yes.
Okay. Remember that this is the fibrous skeleton of the heart. It is very important when we discuss the pathology of the heart. Okay, we'll talk about in a little while also in terms of the excitation and contraction of the heart. So, let's now look at this thing. In order for the myocardium to reduce its surface, we said, and in order to decrease the volume that it encloses, it must have practically all its fibers contract at the same time. Now I'm going to switch and put on a different screen. We're going to move to something else. Okay, you see there a diagram that I have drawn, which tries to show you how the length of the fibers change. Of course, I have not pulled the belly sticking out, right? But this represents a cell. And what I'm trying to tell you in the previous slide is that if you take a cell up on top, and you consider that only part of the surface, so not a cell, if you take the full surface of the heart, and you consider just a part of it contracting at any time, you're going to see some shortening. But as the wave propagates on top of the heart, the volume will decrease a little bit, but it will stay at that point forever until the whole muscle relaxes. On the other hand, if you had a way to make all the muscle of the heart contract simultaneously, then obviously you're going to have a lot more effect. This is to the right side, as you see it. Is that understood what I'm trying to tell you? I'm trying to tell you that unless we have all the fibers of the heart simultaneously contract, then we're not going to succeed in raising the pressure inside the chamber too much. And not only that, but no matter how much work the heart performs from that point on, the volume will not reduce any further as long as the wave propagates from one part to the other. The only way you can make the heart raise sufficient pressures is for its whole surface to reduce at the same time its length, the length of its fibers. Okay? So this repeats what I just told you, that in order for us to achieve sufficient propulsion of the blood, we need the whole surface of the heart to contract at the same time. Τώρα, now, I'm talking a few Greek words get out from me once in a while as I talk to you. Given the time and length constants that we have discussed up to now, and considering for a minute that a cardiac cell behaves like any excitable cell, and given that the cardiac cells do not have myelin sheaths, okay, they behave like unmyelinated fibers. This means that the propagation of the wave across the heart is going to be very, very slow. The situation is really worse than it sounds. Because if you consider the heart as a little bit as the size of your fist, okay? Your heart is it's a little bit bigger than the size of your fist. A real heart is about this, okay? If you look at your fist and you measure it, you'll see that it is about 15 centimeters, 20 centimeters maximum across, which means that no matter where you start, by the time the wave propagates throughout the surface, you need to cover about 30 centimeters of length. This makes it, inside there are many intercalated discs. It's not, in other words, one direct flow, because at the intercalated disc, because the resistance is very high, the length constant drops very much. So it is a very slow movement of the action potential across the surface of the heart. Therefore, there is no way on earth that the heart could achieve simultaneous firing of all the cells that it contains. No way on earth. So, the question that really comes out is, how does it do it?
Pacemaker.
Excuse me?
Pacemaker?
Pacemaker. We are going to get to that, but pacemaker sets the pace. It does not set the velocity, right? Okay. We are going now to talk a little bit jokingly, but in effect, this is what I'm going to show you now. In order to fire all your myocardial cells at the same time, you have to think about how you burn a forest without getting caught. This is a gross joke, but it gives you the reality. I lived in California for too long to know that every summer we are worried about the fire walking up to our yard and burning our house. So I know pretty much about these things, because we always had arsonists that used to set up fires in the forest. Okay. Let's see how they do it, okay? And let's see how the heart does it. You see this diagram? Let's go on the left side. If you're a stupid arsonist, you're going to set up a fire, and let's assume that the fire propagates with a given velocity. It is going to go out in concentric circles, and if this square is the surface of your heart, you'll see that by the time of the fifth time period, still you'll be propagating. I say stupid arsonist because this kind of fire, it's easy to combat. But if you are a real arsonist, one of those that never get caught, you set up the fire in one hand, and you get on an enduro. You know what an enduro is? Is about 1,000 cc bicycle that is for off-road. And you run around the forest, and you set up small fires in many places, and you get out fast. And what happens is, in the first instance, I mean, if you set up 4, you see at the end of the black arrows there, you take a path where we lit fires, and then you see at the first instance the fire will propagate. The second instance, you'll see the new propagation, and the third instance you'll see farther out. In other words, as the fire spreads from many points, it covers the whole area very fast. Do you understand what I'm saying now? Do you see how you can burn a forest very fast? I see you thinking very deeply.
Well, that's good.
What?
I understand. You put fire in every corner, that's why you get more.
Well, that's a different story. You can do it in many ways. I agree with you. There is many ways you can do it. But normally you don't go to put it in many corners. In the far off corners, you have to go there yourself. And this means a lot of transversing and time to get caught. But if you go just through one line through and put a lot of small fires, this is what's going to happen. And that's what most arsonists really do. So, let's see who is the arsonist in the case of the heart. The arsonist is called the specialized conducting system of the heart. And over now, here, over the next slide, take a good look. It is a system of fibers that runs from the sinoatrial node, which is in the upper side of the colored part of the diagram with these little green fibers that you see there, at the back side of the right atrium, above the place where the inferior vena cava empties into the right atrium. You see it? This is the arrow that doesn't have a tag in it, okay? Up on the top left corner as you look at it. Don't get confused that the right atrium is in the upper left corner. You're looking at the heart and the front to back direction. Therefore, it is going to be looking at you like in the mirror. This is not your heart. This is the heart of the person you talk with. Understood? You see it? And then you have the atrioventricular node, which is the next stop in the arsonist's run. And then, in fact, you have two roads that the arsonists somehow, or the arsonists, take both of them and run down all the way to the apex of the heart. And this is called the His bundle. This is the single bundle that goes from the atrioventricular node down to the place where they bifurcate. And then you have the left and right bundle of His, which run on the diaphragm between the muscle diaphragm between the right and the left ventricle, until we reach the apex of the heart, where these bundles break up into the so-called Purkinje fibers, or Purkinje if you follow the French way of pronouncing it. And then these bundles go all the way up to the myocardium until they come back to the top of the atrioventricular valves. That's where, if you recall from the previous slide, the fibrous diaphragm is. In fact, they stop on the fibrous diaphragm. This is why I was telling you, take a good look at it. You are going to need it. Okay? Now, let's diagram that a little bit better. I mean, not that I'm a good artist. What you're going to see is some of my artistic endeavors now. Oops, excuse me. Okay. I'll get back to the other slides. You see this on your right hand side, this diagram, you see the SA node. This was the green, the little green thing that you had up on top, okay? And then you see the AV node. Now over there I have put 3 arrows, because although the previous diagram didn't show it, there are 3 intranodal pathways that join these 2 things together.
What?
Intranodal pathways. Rather internodal. They are between nodes. Internodal pathways. They are not within the node, they are between the nodes. Internodal pathways. Okay? In anatomy you find out that they have names. They are these so-called bundles of Bachmann, and there is a front, middle, and back one. And out of the frontal, the bundle of Bachmann, this is the frontal one, is the main bundle of Bachmann. There is another pathway that goes from the right atrium to the left atrium and lights up the fire there. I know you look at it, and I can see that you're looking at it very confused. I'll explain to you everything. Don't panic yet. Just look at the geometry first. Okay? You see this little blue circle that's made out of little blue lines that are set up in a circle on the right side? Do you see it there?
Yes.
Okay. This corresponds to these rings, this fibrous skeleton of the heart. In other words, as you see it, the Purkinje fibers come up to there and they stop. Okay? Now, let us go back for a minute and talk about this pathway. Because what I outlined for you right now was a pathway, correct or not? It is a pathway that has certain parts. It has the SA node, the 3 internodal branches that end up on the AV node, and then the bundle of His, which splits in 2 legs, which in turn split in the Purkinje fibers near the apex of the heart. Okay? All this bundle is made from cardiac cells that, in contrast to the rest of the cells that contract, these are not very good at contracting, but they are very good in getting the signal very fast across. You see what the difference is? Remember what we said, that on the myocardium the signal will take forever to reach from one side to the other? Yes, and 95-99% of all the cells, except for the cells of this particular system. The cells of this particular system conduct at least 100 times faster than the others. So in effect, they conduct with a speed of about 1 meter per second or even faster. This means that the signal can go from one side of the heart to the other and spread across the whole surface of the heart within maximum 250 milliseconds. So, in effect, what you do is at every small finish, a small point where these Purkinje systems finish, the local myocardial cells pick up the wave, pick up the action potential from the Purkinje cells. So in no time you can light a lot of fires across the whole surface of the heart. Okay? Is it understood how the signal travels very fast on the heart? No, I want to hear it from all of you. If it's not, I really am going to go back.
Can you quickly repeat it?
Excuse me?
More. Can you quickly repeat it once more?
Yes.
That was just like...
I am saying that the heart is made of myocardial cells. The whole heart. Okay? The myocardial cells, let me say it now, I'll repeat it in a minute, are of 3 kinds. They are the cells that do the work. These are the regular myocardial cells. These are the cells that contract. They are very good at contracting. These are the cells that their action potential lasts 250 milliseconds. Okay? Then there are some cells which are called P cells. These are pacemaker cells. We are going to talk about them. And in between the P cells is a whole bunch of other cells which are called intermediate cells. And these are very good at conducting the action potential. In other words, they have very wide, if you want to look at it that way, very wide intercalated discs. They allow the currents to go through the intercalated discs very easily. So they conduct with just about the velocity of an unmyelinated nerve fiber. So in effect, through them, from the SA node where the pacemaker is, to the end of the muscle, the action potential can travel on this pathway within 250 milliseconds maximum. Okay? So that if it will get there before the wave will arrive through all the other intercalated discs of the myocardial cells, of the contractile myocardial cells. Understood? This diagram here, this pathway, is made of specialized cells that conduct the action potential fast. So the action potential arrives at all the unexcited parts of the heart very fast and locally starts spreading, exactly like we said about the forest fire and the arsonist. You understand now why I made the parallel between the arsonist and this system? Everybody or not? I will answer the questions 100 times. This is very important for you to understand. 1/3 of the pathology of the heart is the pathology of this system. Okay, let's go back a little bit. Okay. In this diagram, which you have seen before, now you see that you have the SA node. It translates to sinoatrial node. This is the SA from. Okay? And down below you have the AV node. You don't see it on this diagram, but there are 3 bundles that go between these 2 points. Front, middle,